Welcome back everyone. In this lecture I will go back to the equivalence relation and then we will see the connections between the equivalence relations and the partition of a set. So, let us begin with the definition of equivalence relation. So, we start with a relation, let us say over x. So, let us call it tilde. So, this is a relation over let us say capital X. Recall that a relation is a subset of x cross x. Now, we want to define what is an equivalence relation. So, we call this tilde is an equivalence relation if it satisfies the following properties. So, tilde is called an equivalence relation if the following properties are satisfied. The very first property is reflexive. So, that means any element A in X that is related to itself. So, A related to A for all A in X, and as a second property we have symmetric property. That means, if A is related to B, and that would imply that B is related to A, and this is true for all A B in X. As a third property we have transitivity. So, the transitive property says that whenever A is related to B, B is related to C, that should imply that A is related to C. Again, this is true for all A B C inside X. Okay. So, these three properties should be satisfied: reflexive, symmetric and transitive. So, one way to remember this, we can actually think of equivalence relation as being equal to each other. Okay. For example, if I take this equality, the equality in a set, okay, that actually satisfies all these properties, like so x will be equal to x, and then if x is equal to y, that would imply that y is equal to x, and x is equal to y and y is equal to z, that would imply that x equal to z. Okay. So, you can actually recover all the properties of equivalence relation by remembering that equivalence relation is very much like equality. So, now given equivalence relation, what one can do, one can define what is called equivalence classes associated with that. So, let us actually define them. So, given let us say A in X, and we call this equivalence class of A. So, of course, with respect to that equivalence relation, so most often we actually ignore the dependency on the equivalence relation if it is understood from the context. So, we simply write it as bracket A, which is by definition you collect all elements of capital X that are related to that given element A. So, B is related to A. So, note that it is indeed a subset of X, and this is what we call it as equivalence class associated with A. So, this is what called equivalence class associated to A. So, now what we can do, we can collect all possible equivalence classes and form a set. So, we can collect all of them, the equivalence classes A, where A comes from capital X, and note that all these are all subsets of A. Indeed, this collection is sitting inside power set of X. Okay. And so, this is what we are going to call it as a quotient set. So, this is what called quotient set. Sometime if you are coming from topology point of view, you call it as a quotient space, which is often denoted as x modulo tilde or x comma tilde. So, which is again a set. So, which is a collection of all these equivalence classes that comes from this equivalence relation tilde. So, this is often very important set that will be studied. In practice, what we need to do is we need to identify this quotient set with something known to us. Okay, that is the most important task in working with quotient sets. So, let us do some examples and then see like how one can attempt to do this. So, let us look at some, first of all, some geometric examples, and then we will come to this other algebraic examples. So, let us take for example, R2 like before. So, now what we can do, we can define the following relation. So, we say that x comma y and then z comma w coming from this R2. So, they are related, x y and z w, they are related if and only if. So, we assume that the norm of both these vectors, they are same. That means, x square plus y square is same as z square plus w square. Okay. And it is not very difficult to verify, this is indeed an equivalence relation. So, if we look at it pictorially, so we have this R2 which is drawn like this. So, now you have this unique point which is the origin. So, the norm of the origin is 0. So, if any vector has the norm is 0, that would imply that both the coordinates are 0. If x y, so if x y has the norm 0, that means x square plus y square is 0, that would imply that both x y are 0. Indeed, if and only if. So, that means, so we have this singleton 0 in this equivalence class of 0. So, now let us look at some other element. For example, we can take this 1 comma 0 and then see what are all the elements will be lying there. So, if I take 1 comma 0, so then the norm of this is exactly 1. So, now we want x y related to 1 comma 0. So, that means, if and only if x square plus y square should be 1. So, that means, whatever elements that lie in this circle, so that is going to be related to 1 comma 0, and this is true for other elements as well. So, if we fix this radius, so then you can see that whatever lies in that circle with that radius, so that will be related to given element. Okay. Let us fix x naught and y naught and then look at its equivalence class. So, then it will be collection of all elements x y in R2 such that x square plus y square should be exactly R, where R is x naught square plus y naught square. Okay. So, let us put R square here, that means R is the square root of this. Okay. So, now you can actually see that you can draw this circle of radius R, and then all the elements that lie in that circle is going to be related to that x naught comma y naught. Okay. So, equivalence relations, they are not some random subsets, they will have some geometrical meaning if you are working with some specific examples. So, now you can see that if we take a line, so that indeed passes, so you can take a line segment like this. Okay. For example, we can take this the non-negative part of the x axis. So, if we just simply take this part, so then you can see that that will actually form a indexing set for the quotient set, because each circle is going to intersect exactly at one point with this 0 comma infinity. So, that is this non-negative part of the x axis. So, then you can see that so each equivalence class will have exactly one intersection with this closed 0 comma infinity. So, there is a one-to-one correspondence between this R2 modulo tilde and then this closed 0 comma open infinity. So, there is a one-to-one correspondence between these two. So, this is what I was telling. So, even though like R2 modulo tilde is abstractly defined subset of power set of R2, we can identify that with more meaningful sets like this. So, that is what one should do in practice. So, that is the most important thing. So, let us do some other examples. For example, if we take something like this, which is again motivated from both geometry and group theory, like we can take x to be R, and then we say that x and y from R, they are related if and only if x minus y belongs to the set of integers. So, then we want to actually see what happens to this. So, now we want to actually identify all possible equivalence classes. So, let us draw a diagram. So, we have this real line. So, now we have 0 here, 1 here, 2 here and so on, minus 1 here and then minus 2 here and so on. So, now what we want to do, like we can take some typical element from this and then see what will be the equivalence class. So, let us look at 0 first. So, if we take the equivalence class associated with the 0, this will be all elements x in R such that x and 0 should be related. Now, note that x is related to 0 if and only if x minus 0 must be an element of integers. So, that simply says that x is supposed to be an element of integers. So, that means this is exactly the set of integers that we are getting. So, the equivalence class associated with the 0 is exactly the set of integers. Now, similarly, if we are looking at this 1 by 2, the equivalence class related to this will be those x in R such that x related to 1 by 2, that means x minus 1 by 2 should be an integer. So, now it is not difficult to work out, this is same as all possible elements coming from x in of plus integer. So, that means this is exactly of plus agent. And similarly, if we take any x in R, you can see that the class x is going to be those y in R such that x minus should be in G. So, that would say that those are y minus x we can write here because of the symmetric. So, in particularly you have y minus x belongs to G. So, that implies you are collecting y in R such that y belongs to x plus z. So, that means all you are doing is taking the translation of G by x. So, that means if we are plotting this in the real line. So, if I am taking for example starting with 0. So, then we are getting all the integers. So, coming from the set of integers. Now, if we move from 0 to like 1 by 2. So, then we are getting just all addition of this off with integers. So, you will be getting off 1 and off 2 and off and so on. So, this clearly says that if we are starting from 0 and then move along this direction. So, then you will be just going from this 0 to all the way to up to 1. Then when you reach 1, you are getting again integers. So, that means from 0 to 1. So, this should be your indexing set. So, but the thing is if I take the class associated with 1, that is again the set of integers. So, that means we are supposed to exclude this 1 from this line segment. So, that means what we are having is actually this R mod tilde, which the set of all equivalence classes, which is denoted by the class X, where X comes from R. So, which is same as saying that X plus G, where X coming from R. So, this is, if you think about it, it is parameterized as follows. You take all X plus G such that X now comes from only from 0 to less than 1, because when it hits X equal to 1, you get back G. So, indeed the parameterizing set is actually the closed 0 and open 1 on the right side. So, this is what you are getting it as subset of P of R. So, this clearly like tells you that sometimes one has to use the geometry in order to understand what is the quotient set, and here indeed we are using some algebra. So, similar like examples can be actually constructed. Maybe when we are doing group theory, we will be seeing lot more examples as quotient groups, okay, or quotient sets there also. So, the most important examples, they comes from fibers. Okay. So, one can actually fix a map from X to Y, and then one can actually define a relation X related to Y for X and Y comes from capital X, if and only if they actually take same image. Okay. So, the same value in the image f of x equal to f of y, and it is easy to verify this is indeed an equivalence relations. And what will be the equivalence class associated with the given element? Let us fix some x in X and look at the class X with respect to this relation. Okay. So, this is going to be collecting all possible y in X such that f of x is supposed to be equal to f of y. And if we talk in terms of the pre-image, then this is exactly looking at f inverse of the singleton f of x. Okay. So, these are all the like pre-images of f of x, and that will be the equivalence class associated with this particular equivalence relation. Maybe I will leave one particular thing as exercise. So, let us look at this particular equivalence relation defined on Z cross subset of Z cross Z. So, let us look at this subset m comma n, call it capital X, which is those elements from Z cross Z such that the second coordinate is non-zero. Okay. So, we want to actually realize the rational numbers as quotient of this. So, that is what we are doing. Actually, that is indeed the definition of rational numbers. So, here what we are going to do, we just say that m and n and a and b, they are related if and only if. So, we want to consider that m by n is same as a by b as rational numbers. But let us say that we do not know how to define rational numbers. So, we would like to define rational numbers. So, that means we do not know what is the meaning of a by b. So, in that case what we will do, we can understand the multiplication in integers. So, using that we can say that m b is same as a n. Okay. So, that is the relation that we are going to put. So, we just say that m b is same as a n, and one can check this is indeed an equivalence relation. So, now what will be the equivalence classes? So, if I fix some m comma n and then look at its the equivalence class, you collect all possible a b coming from x such that m b is same as a n. And if you think about it, this actually gives a mapping from this the quotient set to this rational numbers Q, where the mapping is given by the class m n goes to m by n, and one can check that this is indeed well defined map, and this is also a bijective correspondence between them. Okay. So, that means we have this quotient set which is indexed by the rational numbers. Okay. So, this is like again I will be going through this in details later in the course, but here you can see that one can also get more algebraic version of quotient sets. So, now what is the advantage of having this equivalence relation? So, if we take this set of all equivalence classes associated with the given equivalence relation, okay, that will form a partition of a given set X. Okay. So, let us write it as a proportion. So, let us start with some set X with a equivalence relation. So, let us take X to be a set and tilde be an equivalence relation on X. Okay. So, now we can actually look at the equivalence classes. So, what one can prove? So, then we have that either two equivalence classes, either they are identically equal or they are completely disjoint. Okay. So, if we are starting with an equivalence relation, then the equivalence classes have this wonderful property. Okay. So, let us actually start proving this. So, it is enough to prove that whenever this equivalence classes have non-empty intersection, that would imply that both of them are equal. So, let us write down the proof. So, enough to prove that when you take the intersection between these given two equivalence classes non-empty, that should imply that those two equivalence classes are equal. So, let us fix an element Z coming from this intersection. So, now that would imply that Z is related to X and Z is related to Y. Note that we have symmetric and transitive, reflexive, all those properties. So, now we want to prove these two sets are equal. So, to prove those two sets are equal, we need to prove that one set is contained in another and vice versa. Okay. So, by symmetry we can see that it is enough to actually prove one of them, because if the class X intersection class Y is non-empty, that would imply that class Y intersection class X non-empty, and if we prove that class X is contained in class Y, that would imply that class Y is also, similar argument will tell you class Y is also contained in class X. So, now let us claim that. So, the class X is indeed contained in class Y. So, let us start with an element, let us call it W, which is coming from class X, and that would imply W is related to X. Now, note that W is related to X and Z is related to X, and that would imply W related to Z. So, now you can see that W is related to Z and W is Z is related to Y, Z is related to Y. So, that together will imply W is related to Y, and that means W is in the class Y. So, this simply says the class X is contained in class Y. By symmetrical arguments, like I said, we also get class Y is contained in class X. So, that would imply that class X is same as class Y. Okay, this proves either we have these two equivalence classes are equal or they are completely disjoint. So, this means that if we are taking this collection of equivalence classes where X comes from X and this is the quotient set, you can see that this collection. So, as a set, so we do not repeat any elements. So, that means as a collection the class X is either equal to class Y or class X intersection class Y becomes completely empty. So, we can treat them as distinct elements. So, now this collection, so this is going to form a partition of our capital X. Why? Because given X in X, we always have that X is going to be inside class X. So, that means the union of this class X, where class X comes from X modulo tilde, this is going to be capital X. So, this is what we wanted in the first place to be a partition. Now, the second thing that says that whenever class X is different from class Y, so that implies that class X intersection class Y is empty. So, that means, so they are all disjoint and their union is capital X. So, that is the definition of partition. So, that tells that this collection indeed form a partition of X. Okay. Indeed, the converse is also true, like if we start with a partition of capital X, it is not very difficult to define an equivalence relation on capital X whose equivalence classes identify with that partition. Okay. So, let us do that now. So, let us recall what is the partition. So, a partition of X is collection of elements, let us label them X alpha, alpha in lambda. So, it is a family of subsets of capital X. So, this is a family of subsets of capital X, and we call it as a partition if the following conditions satisfy. X is union of X alpha, alpha coming from lambda, and the second condition X alpha intersection X beta is empty for all alpha not equal to beta in lambda. So, for distinct elements we want the sets to be disjoint. And given this, we want to actually define an equivalence relation on capital X, so that these X alphas becomes actually equivalence classes. So, let us do that. So, define the following relation. So, define tilde on capital X as follows. So, now the key point is you treat all the elements that are coming from one particular X alpha, they are all related. And if elements comes from two different X alphas, you say that they are not related. So, you take X and Y in capital X and then see whether X and Y are in X alpha. So, then you declare that X and Y are related. Okay. If X comes from X alpha, Y comes from X beta and alpha not equal to beta. So, then declare that X and Y are not related to Y. Okay. So, now it is not very difficult to see this will form an equivalence relation, and not only that and given X coming from X alpha, look at the class of X, then that will be exactly X alpha. Okay. So, I will leave it as exercise, prove that this tilde is an equivalence relation and these X alphas are the quotient, they form a quotient set X modulo tilde. Okay. They are the equivalence classes associated with this equivalence relation tilde. Okay. So, this is not very hard to prove, I will leave it to you. So, that means whenever you are looking for an partition of a given set, then best way to actually go about it to find an equivalence relation. Okay. And that is going to actually tell you that how to decompose that set into the set of equivalence classes. And many interesting examples actually will come from geometry. So, one should be like comfortable with actually working with them. So maybe I will add more examples in the assignment. Okay, so now let us look at these functions. I want to actually talk about inverse images. They are also very important operation whenever it comes to the functions. So let us say we have a function that is defined from x to y, and yeah, like I said, we want to talk about inverse image. So now what is the inverse image of given subset B of y? So let us take a subset B of y, and then we want to define this inverse image of this B. So which is, by definition, you collect all possible x such that the f of x lies inside B, and this is what you call it as inverse image of B. Okay, of course, with respect to f. So now it is an important thing to actually find inverse images for various subsets. Okay, that actually helps us to understand, for example, the equivalence relation defined using f and so on. So maybe one should actually practice more problems in order to find these inverse images. So let us look at some basic properties, like what happens to the inverse image of union, intersections and so on, and it is not actually very hard to prove. For example, if we take inverse image of B1 union B2, this is going to be exactly equal to f inverse of B1 union f inverse of B2. Okay. And similarly, if we take the intersection, then f inverse of B1 intersection B2 is going to be exactly equal to f inverse of B1 intersection f inverse of B2, and of course, B1 B2, they are all subsets of y. So similarly, one can also look at what happens to in terms of the inclusions and the difference. So if B1 is subset of B2, then it is not hard to see that would imply f inverse of B1 is subset of f inverse of B2. Okay. And similarly, so if I take f inverse of, let us say, y difference B1, so this is going to be exactly equal to x difference f inverse of B1. Okay. So basically the inverse image behaves very well with respect to the set operations. Okay. And it is not actually very difficult to verify these things. So maybe let me do this fourth one, and remaining thing I will leave it as exercise. So what we need to prove? We need to prove that these two sets are equal. So let us start with the left hand side. So the left hand side says that so you take x inside f inverse of y difference B1, and that would imply that f of x is an element of y difference B1. So that means that f of x is not an element of B1. Anyway, the function is defined from x to y. So I don't need to say that f of x is indeed element of y, that is implicitly true. So now this would imply that immediately x is coming from capital X and x is indeed not coming from f inverse of B1. If x is actually comes from f inverse of B1, that would imply that f of x will be in B1. Okay. So that is why we immediately get that x is indeed comes from x difference f inverse of b 1. And if you think about it, all these implications can be reversed. For example, if x is comes from x difference f inverse of b 1, that means x is in x, but x is not in f inverse of b 1. So, that means f of x is going to be in y, but f of x is not going to be in b 1. So, that means f of x is in y difference b 1. So, that means x is in f inverse of y difference b 1. So, that tells you that whenever x is in f inverse of y difference b 1, if and only if x is in x difference f inverse of b 1. So, that means this equality is true. And similarly, one can prove the other relations as well. So, this tells you that the inverse image, this operation indeed behaves very well with respect to the set operations. And one can actually want to find inverse images more explicitly, and that would actually help one to do calculations very well. Okay, I will stop here. We will continue with Jones lemma and so on in the next class. Thank you. I will stop here.